Okay, so I got another request to do homework problem 15.22. Thanks to that student. I forget who asked it. I think it was. Uh-oh. I think it was AH. So either way. This is a question that seems like a really hard one at first. I guess they all seem pretty hard at first, don't they? Generally, the quantization of translational motion is not significant for atoms because of their mass. So in other words, we don't really need to use quantum mechanics for translational motion. First question I think that comes out of something like this is, what is translational motion? Okay, so that's just motion like you just heard, those little footsteps behind me. That's translational motion. That's a little child running across the kitchen as fast as she can. And that's translational motion. And she's way too big to be concerned about dealing with her in terms of quantum mechanics. So we can simply use classical mechanics to deal with Olive. All right. But that's what translational motion is: a little child running across the kitchen, or a molecule going across this box, right? Or a particle going across a one-dimensional box. Okay, that's translational motion, moving. Zeolite, that's another term that shows up in here, and it just gives a definition of it. But I admit that especially in a quiz or exam, you get a term like that, and that's an additional thing just to be scared of, right? But it says zeolites are structures with small pores that we describe by a cube with an edge length of 1.00 nanometers. Okay, so I got a cube here, edge length. Now, if I'm thinking, this is what a zeolite is, by the way. We just talked about a zeolite. Not that it really matters, but okay. So we've got a cube here, and the question's going to be about a molecule inside this box, and this is essentially a 3D particle in a box, three-dimensional particle in a box. And so the edge length is L. So I'm going to do a three-dimensional particle in a box. So I can't just do A. That's for 1D. A and B, that's for 2D, and then A, B, and C, that's for 3D. Okay, and so all the dimensions of this particle in a three-dimensional box are 1 nanometer, which I'm converting right away to 1 times 10 to the negative 9 meters, so that I don't have to worry about that later. All right. So the question is calculate the energy of an H2 molecule with n of x equals n of y equals n of z equals 10. So the energy level for all three dimensions is 10, and we're supposed to calculate the energy. Well, we could do this the long way, which the first time I sat down to solve this problem, I did it the long way, and we know that the energy is complicated, right? That comes from the total energy operator, h bar squared over 2m, that's minus h bar squared over 2m, d dx squared plus velocity component, or rather the potential component. But this is in a box, so there's no potential component. But the reason why that's the Hamiltonian, right? The reason why this is hard is because we have three dimensions. And we go, oh, wait a second, I already derived an equation for this in one dimension, and it was E is equal to h squared n squared over 8 ma squared, right? And this was for a 1D, and so E for 3D, E is going to be h squared n in the x dimension squared over 8 ma squared plus h squared n squared in the y dimension over 8 mb squared, if we're going to let b be the length of the y, plus h squared, I'm out of frame there, aren't I? Z squared over 8mc squared, right? Where that is the length in the c dimension, and in the z dimension, okay? So what I'm going to do is I'm going to go, oh, wait a second. A equals B equals C equals 1 nanometer, 1 times 10 negative 7, 10 negative 9 meters. I'm just going to go ahead and factor all. I'm going to say those. This is the same thing as h squared and x squared plus h squared and y squared plus h squared and z squared over 8ma squared, 8ma squared, 8ma squared, right? Because a, b, and c were all the same. Now I can factor all of this junk out and say this is h squared over 8ma squared times nx squared plus ny squared plus nz squared. Okay? This is the energy for a particle in a box in 3 dimensions. Boom. Wow. Man, it's so much easier than the first time I worked in this. Okay. So we know what h is. It's 6.626 times 10 to the negative 34 joule seconds. I'm saying that out loud because my wife is sitting here and I'm hoping she will be impressed. M.
I am.
Okay. Attempt to say 109 times 10 to the negative 31 kilograms, because that's the mass we're typically used to using. Hopefully someone's watching this video and going, no, wrong. That's not the mass, because we're talking about an H2 particle. Didn't write that down. H2. So what is the mass of an H2 particle? Well, it's 2 times 1.673 times 10 to the negative 27 kilograms, because that's the mass of a proton, right? Which is a hydrogen nucleus times 2, because it's H2, and we don't add in the electrons because that would be insignificant contribution, right? With that 4 sig figs. That's the mass of the H2 molecule. I'm going to go ahead and solve that right now. If I can find my calculator. I'll solve that in a second. Someone's finding my calculator for me. A then, thank you so much. A then is equal to 1 times 10 to the negative 9 meters, right? So we're done. We know that E then is equal to that squared, that's h squared, 6.626 times 10 to the negative 34. 10 squared plus 10 squared plus 10 squared is going to be 300. And those are dimensionless. I meant to say this is, so we're going to have joule squared, second squared, right, because these are squared. And on the bottom we're going to have 8, which is dimensionless. This mass is, just a second here, 1.673 times 10 negative 27. Enter 2 times. 3.346. That doesn't sound right. Oh yeah, times 10 negative 27 kilograms times a squared, which is 1 times 10. That would be negative 18th, right? Meters squared. Okay, so let's get a number for this. I'm going to come up here and make sure my units cancel out. A joule is equal to, remember energy is equal to 1/2 mv squared. So this is going to equal to a kilogram meters squared per second squared, right? So joules squared second squared over kilograms meters squared is the same thing as kilograms squared meters to the 4th over seconds squared, no, to the 4th, right? That's this one. Then seconds squared is here, that's that one. Kilograms in the bottom, that's that one, and then meters squared is here. Okay, so this is apparently is going to be kilograms. Seconds are going to go to seconds squared, and meters are going to go to meters squared, which is a joule. Perfect, that's what I wanted. Okay. This mass is on the bottom, 8 times 1e minus 18 times. 6.626 E34, enter, squared, 300 times. So I get 4.920 times 10 to the negative 21 joules. Okay, that's the energy. Okay. Then the second question here was, is this a system that has to be dealt with in terms of quantum mechanics? And you may recall, at the beginning of chapter 13, we got that question, 15.22 part B. We got that question, and the answer came from is the spacing. There were two criteria. One of them is the wavelength of the particle in relative to, let's see, is it comparable to the phenomena that we're considering. The second one is the energy spacing comparable to KBT, where it's KBT, right? And so we found that if these were roughly the same, the energy spacing, that would be E final minus E initial, which is delta E. If these were roughly the same or in the same order, then we would say that that it's approaching the classical limit. Great thing to review, chapter 13, criteria for quantum mechanics. It was also on your exam. Several people got partial credit on that. I think very few people got full credit, and it comes right out of a paragraph. I'd love you to find that. That's an important question. So this is something really subtle. Surely you're looking at this and going, I have no idea. That is, if you didn't have the gumption to go back and look at that in chapter 13. Okay, so here we go. In order to find that out, we're going to say E. I'm going to say, in order to bump this up one energy level, instead of being 10, 10, 10, I'll call that E initial, right? That was the energy level 10, 10, 10. E final, I'm going to call E 11, 10, 10. That's going to be the next energy level up. You agree? So in order to do that, we're going to take our energy and just do our equation, which we derived on the previous page, h squared nx squared plus ny squared plus nz squared over 8ma squared. A is so we're still in the same box, same pore, whatever, and the mass is still the same. Everything else is still the same, except I'm taking one of these, instead of being 10, I'm going to make it 11. So this becomes h squared over 8ma squared times 121 plus 100 plus 100. I'm just going to take the first one and make it 11 squared instead. Okay, so this is going to be like the next energy level up. If this energy spacing is close, and when I say close, if it's close to KBT, then we're going to say we're approaching the classical limit. So let's look at this. H squared 6.626 times 10 to the negative 34 squared times 321 over 8, forget what that number was, 346 times 10 to the negative 27 kilograms, times 1 times 10 to the negative 18th. I'm leaving all the units off here. I took care of my unit concerns up there. I know I'm dealing with joules, so I'm not going to worry about that here. I'm just going to calculate this number. Let's see what this is. 6.626, 4, enter, squared, 321 times, 8, enter, 3.346, e minus 27, times 1 e minus 18 times divided by, this comes out to 5.26. I guess I should have known that. 5.26 times 10 to the negative 21 joules. That is E2 minus E1. Oops, no, sorry, that's E2. Sorry about that. Right, that's E2. So now what I do is I subtract that from E1. This is E2. So dE is equal to E2 minus E1. And we'll calculate what that number is. We'll calculate what KBT is. Okay, so the difference between these two then comes out to be 3.444 times 10 to the negative 22